Hello there, and welcome to the Sleepy Space Channel. A world thrown out of the solar system would freeze, but it would not simply die. Its surface would lock beneath ice from pole to pole, its oceans would still over, and its very air would eventually fall from the sky as snow. And yet, far below that frozen shell, a sea of liquid water would remain, warmed by the Earth's own inner heat, sheltering the oldest and deepest life on the planet. This is the strange fate of a world that loses its sun, but keeps its warmth. Tonight we follow the Earth out into the dark, through the fading of the light, the freezing of the seas, and the long drift among the stars. If you find these quiet explorations worth your time, a like or a subscribe helps the channel reach others who do. Thank you for being here. But none of this is anything you need to carry into the night. For the next couple of hours, let the cold stay out there among the stars, far from where you are. Settle in. Let your shoulders soften. Let your breathing slow. Let the day fade away. Let's begin. Nothing about the Earth itself would change in the moment it was thrown out of the solar system. The ground would not shake. The sky would not tear open. The mountains would stand exactly where they had always stood, and the oceans would lie in their basins as calm as they had been the hour before. If you had been standing on a hillside at that moment, you would have felt nothing at all. And yet everything would have changed, because the change would not be one of substance. It would be a change of address. The Earth would stop being the third world from a star and become a world that belonged to no star at all. To understand why that single change matters so much, it helps to understand where the Earth gets its warmth. Almost all of it comes from outside, delivered across 93 million miles of empty space as sunlight. The sun pours a little over 1,300 watts onto every square meter that faces it at the top of the atmosphere, and once that light is spread across the whole turning globe and filtered through cloud and air, it still amounts to an average of some 240 watts, reaching every square meter of the surface and the lower sky. That steady flood of light is what holds the world at the temperature life has always known. Against that flood, the Earth's own inner warmth is almost nothing. Heat does rise from the planet's hot interior, leaking up through the crust beneath your feet, but it amounts to less than 1/10 of a single watt for every square meter of the surface. Set the two side by side, and the sunlight outweighs the planet's internal heat by more than 2,000 to 1. The Earth is warm on the outside because of the sun, and warm on the inside for reasons entirely its own, and those two kinds of warmth are almost unimaginably unequal. This is the fact that governs the whole of what follows. To throw the Earth out of the solar system is, above all, to take away its sunlight. And when the sunlight goes, the great outer warmth goes with it, and the surface of the world is left with only that faint inner heat, more than 2,000 times too weak to hold back the cold. The surface, which is the part of the Earth we know best and love most, is also the part that depends most completely on the star it is leaving behind. It is worth being clear from the very start about what this scenario is and what it is not. It is not the destruction of the Earth. The planet would not break apart, or burn, or crumble. It would remain a whole and solid world, the same mass, the same size, the same spinning ball of rock and metal and water it had always been. Its interior would stay hot for billions of years. Its core would keep turning, its mantle would keep flowing, its magnetic field would keep wrapping the planet in its invisible shell. In almost every internal way, the Earth would go on being the Earth. What would change is only the world outside it, and the temperature of its surface, and the slow fate of everything that lived on that surface, under the light of a sun that was no longer there. There is a name for a world that drifts through the galaxy without a star to call its own. Astronomers call it a rogue planet, or sometimes a free-floating planet, or an orphan world. These are not imaginary things. The galaxy is thought to be full of them, worlds that were born beside a star and then cast out to wander alone through the dark between the suns. Many of them were flung from their birthplaces exactly the way the Earth would be flung from ours, in the chaos of a young planetary system finding its balance. Thrown out of the solar system, the Earth would not become something unheard of. It would simply join one of the largest and quietest populations of worlds in the entire galaxy. So this is the journey we will follow tonight, slowly and without alarm. We will watch the light fade and the cold come down. We will follow the freezing of the oceans and the strange, patient freezing of the air itself. We will look at what dies on the surface and, more surprisingly, at what does not die far below it. We will see that the Earth carries its own warmth and its own water out into the dark, and that this changes everything about its fate. And we will follow the frozen world outward, past the edge of the solar system and into the long drift among the stars, to ask what becomes of a planet that has lost its sun but kept its heart. None of it needs to be frightening. The Earth in this story is not a victim and not a ruin. It is a world doing what worlds are made of matter and gravity and heat can do, following the plain rules of physics into an unfamiliar place. There is a strange calm in watching it happen, in seeing how much of the Earth endures even when the one thing we thought it could not live without is taken away. And so we begin where the story begins, with a world lifted gently from its place beside the sun, and the first long silence as the light starts to fade. It is worth pausing on just how deep the coming cold would be, because the numbers are hard to hold in the mind. The average temperature of the Earth's surface today is about 59 degrees on the Fahrenheit scale, a little under 15 degrees Celsius, mild enough for open water and green fields across much of the world. Strip away the sunlight and leave the surface with only the planet's own inner heat to warm it, and the temperature it would eventually settle toward is somewhere near 400 degrees below 0 Fahrenheit, close to the natural cold of deep space itself. That is not a matter of a harsh winter. It is a cold more than 200 degrees below the freezing point of water, a cold in which the very air would eventually turn to frost and fall to the ground. Between the warm world of today and that final frozen one lies the whole of the journey we are about to take. There is one more thing worth settling before we go on, and it is the difference between two scenarios that sound alike. People sometimes imagine the sun simply switching off, blinking out where it stands. What we are following here is a little different, and in one way gentler. The sun does not vanish. Instead, the Earth is pulled away from it, carried outward on a new path, so that the star does not disappear but recedes, shrinking and dimming as the distance grows. The end result for the surface is much the same, a world losing its light and its warmth. But the Earth in our story is also moving, gaining a direction and a speed, setting out on an actual voyage into the dark, rather than simply being abandoned in place. That motion, as we will see, becomes a story of its own. A planet does not leave its star easily. The Earth is held in its orbit by the sun's gravity, bound as firmly as a stone whirled on a string, and left to itself, it would keep circling for as long as the sun endured. To grasp how firmly it is held, it helps to think in terms of speed. The Earth travels around the sun at just under 30 kilometers every second, a little more than 66,000 miles an hour, fast enough to cross the width of a country between two breaths. Yet to break free of the sun entirely from where the Earth sits, it would need to be moving faster still, at around 42 kilometers a second. The planet is bound by a wide margin, and nothing it does on its own can close that gap. Something from outside has to reach in and give it a push. That push can only come from gravity, from the pull of some other massive body swinging close enough to change the Earth's path. And there are a few real ways this can happen, none of them fanciful, all of them known to occur among the stars. We will walk through them slowly, not because the exact cause matters greatly to the frozen world that results, but because it is worth seeing that the galaxy really does throw planets out, and has done so countless times. The first way is a close pass by another star. The stars are not fixed lamps hung in place. They drift, each on its own long orbit around the center of the galaxy, and over spans of hundreds of thousands and millions of years, other stars wander through the sun's wider neighborhood. Almost always they stay far away, light years distant, their influence too faint to feel. But given enough time, the odds allow for a closer pass, near enough to disturb the cold outer fringes of the sun's domain. A star sweeping through at just the wrong distance could stir the planets from their steady paths, stretch their orbits, and set them on courses that cross one another. In rare cases, such a disturbance ends with a world flung loose entirely. The chance for any single planet in any single pass is small, but stretched across the lifetime of a planetary system, small chances add up. The second way is more common, and it is the one that models of young star systems show again and again. It is a slingshot off a giant planet from within the same system. If the orbits of the large planets ever fall out of their careful balance, worlds can be drawn into close encounters with one another, and when a smaller planet swings near a giant, the giant's gravity can hurl it outward with tremendous force. It is the same trick that spacecraft use on purpose, borrowing a little speed from a planet they fly past, except turned up to a violence no engineer would ever choose. The giant loses the faintest trace of its own motion, so slight it would never be noticed. The small world gains enough to be thrown clean out of the system. In our own solar system, the planet Jupiter carries more than enough mass to do this. Many of the rogue worlds now drifting through the galaxy are thought to have been cast out in just this way, early in their system's violent youth. The third way belongs to the far future and to the sun's own old age. Stars do not last forever, and near the end of its life the sun will change dramatically. It will swell into a red giant, growing immense and luminous, and it will shed a great fraction of its own substance into space. When a star loses mass, its gravitational grip weakens, and the orbits of whatever planets remain grow wider and more unstable. In that late and unsettled era, the outer worlds could jostle one another into chaos, and a planet or two could be ejected outright. This is a distant prospect, billions of years away, and by the time it arrives, the swelling sun will likely already have scorched or swallowed the innermost planets. But it shows that even a calm and steady star can, at the very end, let its children go. For the story we are telling, though, the mechanism matters far less than the moment it produces. Whether by a passing star, or a slingshot off a giant, or the death throes of the sun itself, the essential event is always the same. The Earth receives a gravitational shove. Its speed relative to the sun climbs past that critical threshold of escape. And it begins the long climb outward, no longer circling but leaving. It is important to picture that departure correctly, because it is not like a rocket launch. The Earth would not roar away under continuous power. It would coast, moving under its own momentum, and as it climbed away from the sun, it would actually slow, fighting against the star's fading pull, the way a ball thrown upward slows as it rises. But if the push was strong enough, the Earth would never fall back. It would keep climbing, more and more slowly, until it reached the outer edges of the solar system with a modest speed still left in it. And then, past the last influence of the sun, it would settle into a steady coast, drifting outward at a few tens of kilometers a second, carried on into the dark by nothing more than the motion it was given at the start. From that moment, the Earth's fate is sealed in the simplest possible way. The light that warms it is falling behind. The distance is opening. And a world that has known only the steady presence of its star is about to learn what it means to lose it. There is a quiet elegance in the way a slingshot works, worth lingering on for a moment. When a small world is flung outward by a giant, nothing is created from nothing. The energy the small planet gains is very nearly the energy the giant loses, passed from one to the other across the empty space between them by the pull of gravity alone. The giant is so much more massive that its share of the exchange barely moves it, the way a great ship is hardly slowed by the wake of a small boat. But for the small world, the same exchange is everything, the difference between a bound orbit and an open road out of the system. It is the same balance that lets a stone be skipped far across a pond while the whole pond scarcely stirs. The threshold the Earth must cross is set by a simple relationship. The speed needed to escape a star is always about 1 2/5 times the speed of a circular orbit at the same distance, the square root of 2, a number woven through the mathematics of gravity. That is why the Earth's orbital speed of nearly 30 kilometers a second and its escape speed of around 42 stand in exactly that ratio. To be thrown out, the Earth need not double its speed or triple it. It needs only to be lifted across that modest gap, and the rest follows on its own. One more detail is worth carrying forward. When a planet is ejected, it need not leave alone. A world with a moon can be thrown out with its moon still bound to it, the two of them cast into the dark together, provided the encounter that flings them free is not so close and so violent that it tears them apart. And whatever path the Earth takes out of the solar system, it would never truly be free of all gravity. It would remain a citizen of the galaxy, still bound to the enormous slow wheel of the Milky Way, orbiting the distant galactic center, along with every star and every world, carried onward in the great rotation that governs everything. In the first hours after the Earth was set loose, almost nothing would seem wrong. The sun would still hang in the sky, still bright, still warm on the skin, and a person watching a sunset that first evening would see the same colors they had always seen. The change would be there, but it would be slow, and it would begin so gently that only instruments could measure it at first. This is because the Earth, coasting outward, would move away from the sun at roughly the speed it once traveled around it, covering the original distance between them only over the span of a couple of months. For a while, the sun would simply be a little farther each day, a little smaller, a little less fierce. But the physics of light is unforgiving in the long run. The brightness of the sun falls away with the square of the distance, so that when the Earth had drifted to twice its starting distance, the sunlight would be only a quarter as strong. At 5 times the distance, it would be a 25th. At 10 times, a mere 100th of what it had been. The sun would not go out. It would dwindle, week by week, from the great warm disk that had ruled every sky in the planet's history, down toward a smaller and colder thing, and the warmth it carried would drain away far faster than the light. The cooling would begin at once, but the surface would not plunge to its final temperature overnight, and the reason is one of the quiet mercies of this whole story. The Earth holds an enormous reservoir of stored heat, banked in its rocks, its soil, and above all, its water. That stored warmth cannot hold off the cold forever, but it can slow the fall, releasing itself gradually as the surface radiates its heat away into a darkening sky. The world would cool the way a great stone house cools after the fire goes out, not in an instant, but over a long and deepening chill. Within the first week, the average temperature across the whole surface of the Earth would drop below the freezing point of water. That average hides a great unevenness, for the cold would not arrive everywhere at the same pace. It would bite first and hardest in two kinds of places, on the night side of the turning planet and deep in the interiors of the great continents, far from the softening influence of the sea. In the heart of a winter continent, the temperature could fall with frightening speed. Along the coasts and across the tropics, where the sprawling warm ocean lay close at hand, the chill would come more slowly, held back for a time by all the heat the water had stored through ages of sunlight. By the end of the first few weeks, the average temperature of the world would have sunk well below anything in the present climate, colder than the coldest place on the Earth today, and it would still be falling. The land would begin to lock into a hard and growing freeze. Rivers would still their currents beneath skins of ice. Lakes would harden from their edges inward. The soil would begin to freeze downward, deeper than any frost that a natural winter had ever reached. And yet, through all of this, the sky would not fall still. The weather would go on, because weather is driven by differences in temperature, and there would still be differences to drive it. The great warm oceans, still liquid, still holding their heat, would become the engines of the world's weather in a way they had never quite been before. Moisture and warmth would rise from the seas into the cold air above, and it would fall again as snow across a world that no longer had a sunrise. For a time, there would be storms in the dark, clouds moving over a lightless world, snow drifting down onto frozen ground under a sky lit only by the shrinking sun and the unchanged stars. The living surface, though, would already be in its final season. Plants would be among the very first things to fail, and they would fail for a reason that runs to the root of how the living world is built. Green plants live by capturing sunlight, weaving it into food through the quiet chemistry of photosynthesis, and without light that chemistry stops. In the dark, and in the spreading cold, the plants of the world would die within days and weeks. The forests would not fall at once, but the green would go out of them, and nothing would replace it. In the sunlit surface waters of the oceans, the boundless drifting clouds of tiny plant-like plankton, which quietly feed nearly the whole of the sea, would die just as quickly. This is a more serious thing than it might sound, because those plants and that plankton are the foundation on which almost all other life is built. They are the primary producers, the ones that make food from light, and everything else in the end eats them or eats something that ate them. When the foundation is pulled away in a single season, the whole structure above it begins to come down. The great animals of the world, even the largest and most powerful, would find their food vanishing within months, and the deepening cold would finish what hunger began. The surface of the earth, so crowded with life, would begin to grow quiet. None of this would happen with drama or noise. It would happen the way frost happens, silently, steadily, a little more each night. The sun would shrink. The cold would deepen. The snow would fall in the dark. And the world would slip, without a struggle, out of the age of sunlight it had lived in since the beginning, and into the long cold that lay ahead. It is worth understanding why the oceans matter so much in these first weeks, because they will matter even more in the years to come. Water is a remarkable substance for holding heat. It takes in a great deal of warmth for every degree its temperature rises, and gives that warmth back slowly as it cools. The world ocean, miles deep and spread across most of the planet, holds thousands of times more heat than all the air of the atmosphere combined. That is why the sea becomes the planet's temporary furnace once the sun is gone, and why the last warm places on the darkening surface would be the ones nearest to deep water. The interior of a continent has nothing beneath it but cold rock, and it freezes fast. A coast leans against an ocean's worth of stored summer, and it holds on far longer. The receding of the sun can be marked, if one likes, by the familiar signposts of the solar system. Coasting outward at its steady speed, the Earth would reach the distance of Jupiter in roughly 5 years, and the distance of the far outer planet Neptune in a little over a decade. At Neptune's distance, the sun's light is already only about 1/900th of its strength at the Earth, still bright enough to read a book by, but far, far too feeble to warm a world. So within the first few years of its journey, before it had even left the outer reaches of its old neighborhood, the Earth's surface would already be receiving almost none of the warmth it had lived on. The deep freeze would be well underway while the planet was still, in cosmic terms, close to home. The freezing would spread from the poles and the night side toward the last warm equator and the retreating daylight, until there was no warm place left anywhere on the open surface of the world. As the months turned into a year and the sun dwindled to a single brilliant point among the stars, the surface of the Earth would settle into a cold beyond anything in its long history. Within that first year, the average temperature across the whole planet would fall to somewhere near 100 degrees below zero on the Celsius scale, and it would keep sinking from there. The old familiar order of the world would already be gone. There would be no tropics and no temperate lands, no summer and no winter in any way that meant anything, only a single, slow deepening of the cold, spreading from the poles toward the equator and rising up out of the frozen ground. The land would grow utterly still. Every river would be frozen along its whole length, every lake solid from surface to bed. The soil would freeze downward, far past the depth of any natural permafrost, the cold reaching meter after meter into the ground as the years passed, until the frozen layer ran deeper than the tallest buildings humans had ever raised. The bare rock of the mountains and the open plains, no longer warmed by any day, would radiate its heat away into the black sky and cool steadily toward the temperature of the space around it. On the land there would be nothing to slow the fall, no reservoir of stored warmth beneath, only the faint trickle of the planet's inner heat rising from far below, so weak against the surface cold that it might as well not have been there at all. The great exception, the one place that fought the cold, would be the oceans, and their surfaces would now be freezing over across the entire world. Today, sea ice caps only the polar oceans, a white lid at the top and bottom of the globe. On the darkened Earth, that lid would spread. Ice would form and thicken across every sea, creeping out from the poles and inward from the shores, until at last the whole surface of the world ocean lay sealed beneath a continuous crust of ice. This freezing over is one of the most important turning points in the entire story, and the reason is a quiet property of ice that changes everything that follows. Ice is a fine insulator. The moment the sea locks beneath a solid roof, it stops losing its heat quickly to the frozen air above, and the water below is sealed away from the worst of the cold. Above that spreading crust, the air itself would begin to change its character. With the oceans sealing over, the great source of moisture that had fed the snows would slowly be shut off, and the weather that had raged through the first months would begin to quiet. The winds would still move, stirred now by the last unevenness in the escaping warmth, but the storms would weaken and the snows would thin as the whole planet drew nearer to a single, uniform, unbroken cold. The world would be growing not only colder, but stiller, the restless machinery of its weather winding slowly down toward silence. Even the composition of the air would start, faintly, to shift. As the surface cooled past certain thresholds, some of the gases in the atmosphere would begin to reach temperatures at which they no longer wished to remain gases. The first to feel it would be carbon dioxide, that small but familiar part of the air which freezes directly into a solid, the same dry ice frost seen curling off a block in a magician's hand, once the temperature falls to around 78 degrees below zero on the Celsius scale. In the coldest places, on the high plateaus and the deep night side, a thin rime of frozen carbon dioxide would begin to gather on the ground, the very first hint that the atmosphere itself was not immune to the cold, and that in the long run, even the air would come down. By the end of that first year, the Earth would already be a changed world to look upon. Seen from far away, it would be a pale thing, wrapped in ice from pole to pole, its oceans white, its continents locked in frost, its air clear and thin and bitterly cold. The blue planet would have become a silver one. The sun that had lit it would be only a bright star now, giving no more warmth than any other point in the sky. And a person standing on that frozen surface, if they could have survived to stand there, would have looked up into a permanent night and seen no sunrise coming, only the slow wheeling of the same old stars over a world of ice. And yet, for all of that, the Earth would not be dead. This is the thing to hold on to as the surface freezes, the fact that saves the whole story from being one of simple loss. Beneath the ice, in the deep water and deeper rock, the planet would still be warm. The freezing that had conquered the surface would stop at the ice, and below it, the ocean would still hold liquid water, and below that, the rock would still be hot, and in those hidden places, the real fate of the Earth and of its life would go on being decided. The surface belonged to the age of the sun, and the surface had ended. But the Earth was more than its surface, and the rest of it endured. To feel the depth of that first-year cold, it helps to reach for the coldest places the Earth has ever known. The lowest temperatures ever measured at the surface, on the high ice of the Antarctic plateau in the dead of the polar night, come near 100 degrees below zero on the Celsius scale. On the ejected Earth, that would no longer be the record set by one cruel spot in one cruel season. It would be roughly the average of the entire planet, every continent and every frozen sea, all at once, and only a waypoint on the road to colder still. The whole world would become, in effect, a single endless Antarctic night, and then grow colder than any Antarctic night had ever been. There is a strange irony in the spreading sea ice. On the Earth we know, the white of ice and snow matters enormously because it reflects sunlight back into space, cooling the planet by throwing away the warmth that falls on it. On the darkened Earth, that reflecting power would mean nothing, because there would be no sunlight left to reflect. The ice would matter for the opposite reason entirely. Its value now would lie in how poorly it lets heat pass through it, in its power to insulate. Even a thin skin of ice sharply slows the escape of heat from the water beneath, and as the crust thickened, it would seal the ocean's warmth in more and more effectively, a blanket laid over the last liquid water of the world. The water cycle itself would not so much stop as simplify and slow. Rain would end everywhere, for there would be no warmth to hold water as vapor for long. What moisture still rose from the last open cracks and leads in the ice would fall again as snow, and nothing else. And as the cold grew even between the equator and the poles, the difference in temperature that had always driven the world's great winds would shrink toward nothing, and with it, the wind itself would fade. The planet was moving, slowly and without haste, toward a stillness it had never known in all its billions of years beneath the sun. The oceans are the reason a world thrown out of the solar system does not simply become a lifeless block of ice, and to understand why, one has to understand something a little peculiar about water itself. Water protects its own depths. When most substances grow cold and turn solid, they become denser than their liquid form and sink. If water behaved that way, the story of the ejected Earth would be far bleaker, for the seas would freeze from the bottom upward, ice piling up from the sea floor until the whole ocean was solid through. But water does the opposite. When it freezes, it expands and grows lighter, and so its ice floats. That single strange fact is what allows an ocean to survive beneath the cold. When the surface of the sea froze, the ice would form a floating lid across the top of the water, and that lid would insulate everything beneath it. Heat would still escape upward through the ice and into the frozen air, but slowly, far more slowly than it would have escaped from open water lying exposed to a black and freezing sky. The ocean would go on losing warmth, but at a fraction of the rate, and the deep water below would be sheltered from the worst of the cold above by nothing more than a growing roof of its own frozen self. Beneath that roof, two sources of warmth would keep the deep water liquid. The first is the ocean's own enormous store of heat, banked over ages and now sealed in beneath the ice. The second, and the one that lasts, is the warmth rising steadily from the planet's interior, the same geothermal heat that today drives the volcanoes and warms the rocks of the deep sea floor. That inner heat does not depend on the sun in any way whatsoever. It comes from the slow cooling of the Earth's molten core and from the natural decay of radioactive elements locked in the rock, and it will keep flowing for billions of years, sunlit sky or not. It is far too weak to warm the open surface of the world, as we have seen, but sealed beneath a thick insulating lid of ice, it is more than enough to hold a layer of the sea from freezing. So the ocean would freeze from the top down, and it would do so slowly, over a very long time. In the first years, the ice would grow from a thin skin into a shell tens of meters thick, then hundreds. Over centuries and then over thousands of years, that shell would thicken further still, perhaps reaching a kilometer or more in depth. But beneath it, warmed from below and roofed from above, a layer of liquid seawater could remain for a remarkably long span of time, for thousands of years at the least, and near the hottest parts of the sea floor, where the planet's inner heat wells up most strongly, for very much longer than that. Here is the quiet wonder at the center of this whole story. That arrangement, a deep ocean of liquid water held beneath a thick shell of ice, warmed not by any sun, but by the heat of a world's own interior, is not something strange or unheard of. It exists right now, in our own solar system, on several of the moons that circle the giant planets. There are small frozen worlds out in the cold and the dark, far from any real warmth of sunlight, that hide entire oceans of liquid water beneath their icy skins, kept from freezing by the heat within them. These are among the most intriguing places known, precisely because where there is liquid water and warmth, there is at least the possibility of life. An ejected Earth would become the greatest of these ocean beneath ice worlds. It would be far larger than any icy moon, with a far deeper ocean and a far hotter interior, and it would carry that hidden sea out into the spaces between the stars. From the outside, it would look utterly frozen, a silver ball of ice adrift in the dark. But it would be a frozen world wrapped around a liquid one, a shell of ice around a living sea, and everything about whether anything could survive the loss of the sun would come down to that buried ocean, and to how long the warmth beneath it could last. It is worth dwelling on the peculiar behavior of water a little longer, because so much depends on it. Cold water grows denser as it chills, and sinks, but only down to a point. At about 4 degrees above freezing, water reaches its greatest density, and if it cools any further, it begins, strangely, to grow lighter again. So, the very coldest water rises to the top, and it is there, at the surface, that the ice first forms, floating where it is made. Beneath it, slightly warmer and slightly heavier water settles into the depths. This is why lakes and oceans freeze from their surfaces downward rather than from their beds upward, and it is why, on the darkened earth, the deepest water would be the last of all to turn to ice. Almost every other common substance in the universe would betray a world in the cold, freezing solid from the bottom up. Water alone builds a floating roof over its own depths and shelters them. The thickness that the ice shell finally reached would be set by a slow balance between two flows of heat. From below, the planet's inner warmth would push steadily upward, trying to keep the water liquid. From above, that same heat would leak away through the ice and into the frozen air, trying to freeze the water solid. Where those two flows met, the underside of the ice would settle, thickening until the heat rising from within was just balanced by the heat escaping to the cold. A hotter interior means a thinner shell and a deeper sea below it. A cooler one means the ice grows down further before the balance is struck. As the ages passed and the planet's inner heat slowly waned, that balance would shift and the ice would reach a little deeper, century by century, toward the sea beneath. The sea itself would fight to stay liquid in ways beyond the simple heat of the deep. Ocean water is salt water, and salt lowers the temperature at which water freezes. As the ice formed at the surface, it would squeeze out much of its salt, leaving behind pockets and channels of intensely salty, intensely cold brine that could stay liquid even where pure water would have frozen. Threaded through the ice and gathered beneath it, these briny veins would be among the last liquid water near the surface, tiny refuges of the unfrozen in a world of ice. And in the crushing pressure of the deep ocean, water behaves in still other ways, the great weight of the sea above changing the very temperature at which ice can form, so that the relationship between cold and freezing is not quite the same at the bottom as it is at the top. Consider then where the story has arrived, because it is worth gathering up before we go on. The sun is gone, shrunk to a star. The surface of the world is frozen from pole to pole, the land locked in permafrost, the air growing thin and beginning to snow out its own gases. And yet beneath the ice lies a living ocean of liquid water, warmed from within, sealed beneath a roof that grows only slowly, a sea that could endure for thousands of years and more. The earth has not died. It has drawn its warmth and its water inward, down beneath the ice, and it is there, in the dark and the pressure and the quiet, that we must look to find what survives. There is a final stage in the freezing of an ejected Earth, one so extreme that it would unfold only after the surface had grown colder than almost anywhere in the present solar system. Given enough time in the dark, the air itself would freeze. It is a strange thing to picture, the atmosphere coming down, but it follows from the same plain physics as everything else. The air is made of gases, and gases remain gases only because they are warm enough to stay that way. Chill them far enough, and they turn first to liquid and then to solid, gathering on the ground as frost and falling from the sky as snow. The atmosphere of the Earth is not exempt from the cold. It is only waiting for a cold deep enough to claim it. The gases would not all freeze at once. Each has its own temperature at which it surrenders, and so the atmosphere would come down in stages, layer by layer, over a very long time. Water vapor goes first, long before the rest, snowing out as ordinary ice, while the world is still relatively warm. Carbon dioxide follows, freezing into that dry ice frost once the surface passes around 78 degrees below zero on the Celsius scale. But the main body of the air, the great mass of it, is something else entirely, and it holds on far longer because it is made of the two gases that are hardest of all to freeze. Nearly 4/5 of the atmosphere is nitrogen, and most of the rest is oxygen, and both remain gases down to astonishing depths of cold. Oxygen does not freeze until the temperature falls to around 218 degrees below zero on the Celsius scale. Nitrogen, which makes up the bulk of the air, holds out until about 210 degrees below zero. These are temperatures far beyond any natural cold the Earth has ever known, colder than the surface of most of the outer planets, and the surface would have to shed an enormous amount of heat before it reached them. But on a world adrift in interstellar space, with no sun and only the last of its inner warmth to slow the fall, those temperatures would come. And as they came, the air would begin to condense onto the ground. First it would fall as a strange dew, and then a stranger snow, the oxygen and the nitrogen liquefying and freezing out of the sky, settling over the frozen sea and the frozen land in pale drifts. Layer by layer, the atmosphere would thin as its substance was laid down on the surface, the air pressure dropping lower and lower as more of the sky came down to Earth. In the end, over many thousands of years, the great ocean of air that had wrapped the planet since almost the beginning would be gone from the sky and spread instead across the ground, a frozen blanket of nitrogen and oxygen snow lying over the older ice of the frozen sea. This would not be a sudden collapse, but a slow and self-slowing one, and that is worth understanding. Each layer of frozen air that settled on the surface would itself act as a little more insulation, trapping a little more of the planet's inner heat, and so slowing the cooling that would freeze the next layer. The atmosphere would fight its own falling, in a sense, each stage of its collapse, buying a little time for the rest. For a long stretch of the planet's dark history then, the Earth would keep a real if thinning atmosphere, growing colder and quieter across the ages, but not yet fully fallen. The final freezing of the air is an endpoint reached slowly, over spans of thousands of years, not a curtain dropped in a night. Imagine standing on that surface in the far cold era, if a body could somehow endure it. Overhead, there would be a sky of perfect black, crowded edge to edge with stars that did not so much as flicker, for there would be almost no air left to make them twinkle. Underfoot there would be pale drifts of frozen air, nitrogen and oxygen snow lying over the deep blue-white of ancient sea ice. There would be no wind, because there would be almost no atmosphere left to move. There would be no sound at all, because sound needs air to carry it, and the air would be lying frozen on the ground. It would be a world of the most complete stillness imaginable, a silence deeper than any silence the Earth had ever held. And far below all of it, still hidden, still sealed beneath the ice, the last warm sea would go on holding its heat, the one restless thing left in a world that had otherwise gone entirely, perfectly quiet. There is something almost fitting in where the nitrogen would end up, for the Earth would not be the first world to wear a coat of frozen air. Out at the cold edges of the solar system, on the distant world Pluto, and on the great moon Triton that circles Neptune, nitrogen already lies frozen across the surface in pale, bright plains. On those worlds, the cold is deep enough that nitrogen behaves the way water behaves on Earth, gathering as frost, building into sheets, even creeping and flowing over ages in slow glaciers of frozen air. The ejected Earth would join that company. The nitrogen that had filled its skies and its lungs and its winds since the beginning would settle at last into plains of pale ice, no different in kind from the frozen nitrogen that already glimmers on the far worlds of our own sun. As the atmosphere came down, the sky would sharpen in a way no earthly sky has ever been sharp. The air we live beneath scatters starlight and paints the space between the stars a faint grey, and it stirs the light of each star into a restless twinkle. With that air frozen onto the ground, the black between the stars would grow truly black, and every star would burn with a hard, steady, unwavering light. In losing its atmosphere, the frozen Earth would gain one of the clearest views of the universe that any surface could offer, a flat black dome packed with unblinking suns, seen through no air at all. The loss of the air would strip away the planet's last shielding too. The atmosphere protects the surface from the thin rain of tiny meteoroids and from the drizzle of cosmic rays crossing space, and with it gone, the surface would lie bare to both. But on a frozen, lifeless surface, neither would matter much. There would be nothing left up there to harm. And it is worth remembering that the atmosphere, in falling, would not be lost. Its substance would not escape into space, but would simply move from the sky to the ground, laid down as snow and frost. The Earth would keep all of its air. It would only wear it differently, no longer as a breathable ocean overhead, but as a pale, frozen mantle underfoot, waiting out the long dark with the rest of the sleeping world. For the living things on the surface of the Earth, the loss of the sun would be swift and complete, and it is worth facing that plainly before turning to the more hopeful part of the story. Nearly all life on the surface of the world runs, in the end, on sunlight. The green plants of the land and the drifting plankton of the seas capture the light and turn it into food, building the sugars and tissues that feed everything else. The animals eat the plants, or eat the animals that ate the plants, and so the energy of sunlight flows upward through every living thing. Pull the light away, and the whole of that great structure loses its foundation in a single stroke. The plants would go first, as we have seen, dying within days and weeks as the darkness stopped their photosynthesis and the cold killed what the darkness had not. The great forests would stand for a while yet as frozen skeletons, but the life would be gone out of them. In the surface waters of the oceans, the clouds of tiny phytoplankton that quietly produce so much of the world's food and so much of its oxygen would die just as fast, their sunlit engine switched off. With the primary producers gone, the food web would come apart from the bottom upward, the way a tower comes down when its base is pulled away. The animals would follow, each in its turn. The creatures that ate plants would find their food vanishing within a single season, and the creatures that ate those creatures would find their own meals disappearing soon after. Even the largest and most formidable animals, the ones that seem to fear nothing, would find themselves in a world with less and less to eat, and the deepening cold would finish what the hunger began. It would not take long in the span of things. Within the first year, the great chorus of surface life, the birds and the beasts and the fish of the sunlit sea, would fall silent. The surface of the world, so extraordinarily crowded with living things, would grow still. A few surface creatures are almost unreasonably hard to kill, and they deserve their mention. There are microbes that can survive being frozen solid, that live in the dry, frozen valleys and the high glaciers, that can shut themselves down into a kind of suspended state and wait out conditions that would destroy almost anything else. There are tiny animals, the tardigrades among them, that can dry out or freeze and endure in that dormant state for a very long time. Some of these could persist, frozen into the ice of the darkened earth, their inner workings all but stopped, neither truly alive nor quite dead, waiting for a warmth that would not come. Seeds and spores could lie in the frozen ground the same way, holding their promise of life in a sleep that might last for ages. But it is important to be honest about what that kind of survival is. To be frozen and dormant is not to be living, not really. The waiting spore does not grow, does not feed, does not reproduce, does not change. It only endures, a sealed message with no one to read it. A world that keeps only frozen, dormant cells in its surface ice has still lost its living surface, even if a scattering of those cells could, in principle, be woken again. The surface would become a kind of tremendous, cold library of life, its books intact but closed, its pages holding the memory of a living world rather than a living world itself. That is the honest reckoning of the surface, and it draws a clear and important line. The surface of the earth is the part that truly depends on the sun, and it is the part that ends when the sun is lost. Everything that lives in the open air and the sunlit water belongs to the age of sunlight, and that age would close. But the surface is not the whole of the earth, and the sun's light never reached the whole of the earth's life. What survives the loss of the sun survives below, in places the light had never touched, and it survives for a simple and remarkable reason. It survives because it never needed the sun in the first place. And it is to those deep and hidden places, and to the life that endures there, that we turn now. It is notable when you look closely how total the surface world's dependence on light really is. Nearly every calorie of food energy in every surface ecosystem, on the land and in the sunlit sea, can be traced back to the single act of photosynthesis, to some green thing catching light and building sugar from it. A mushroom on a forest floor lives on the remains of plants. A wolf lives on the deer that lived on the grass. A whale lives on the swarms of tiny creatures that lived on the plankton that lived on the light. There are almost no exceptions on the open surface. Remove the light, and you do not merely inconvenience this world. You cut the single thread from which nearly all of it hangs. The plankton deserve a last word, because they are easy to overlook and impossible to overstate. These drifting, mostly invisible specks in the upper ocean are among the most important living things on the planet. They sit at the base of the entire marine food web, feeding everything from the smallest fish to the largest whales, and in the course of their sunlit lives, they release a great share of the oxygen that every breathing creature depends on. When the light failed, they would be among the very first to die, and their dying would ripple upward and outward through every ocean, emptying the seas of their abundance within a single season, long before the water itself had finished freezing over. And yet even in this reckoning there is one exception that points forward to the rest of the story. Among all the surface creatures, human beings alone hold the strange power to carry a piece of the living surface downward with them, into sheltered, heated, lighted places of their own making, powered by something other than the sun. Whether that power could be enough to matter is a question for later. For now, it is enough to notice that when the surface froze and fell silent, it would not necessarily take every last living thing with it, because some of the life of the surface might choose, deliberately, to go below, and below was exactly where life could still endure. The surface then closes one chapter and quietly opens another. The age of sunlight ends above the ice, and the age of inner warmth begins below it. Beneath the sea floor and deep within the rock of the world, there is a kind of life that has never seen the sun and has never needed it, and it is there, in the dark and the warmth below, that the Earth's living story would make its stand. On the floor of the ocean, in places where the crust is thin and the heat of the interior rises close to the surface, there are openings from which superheated, mineral-laden water pours up out of the planet. They are called hydrothermal vents, and around them, in the crushing dark of the deep sea, live some of the strangest and most self-sufficient communities of life on the Earth. The creatures of the vents do not live on sunlight, not even at a distance. They live on chemistry. The water rising from below carries dissolved minerals and gases, and certain microbes have learned to draw energy directly from the chemical reactions those substances make possible, building their bodies from that energy the way a plant builds its body from light. Around those microbes gathers a whole community, larger creatures that graze on the microbial mats or filter them from the water, and larger creatures still that feed on those. Ghostly pale crabs, dense thickets of tube worms, blind shrimp, and drifting things without names crowd around the warmth of the vents, an entire living world running on the heat and the chemistry of the planet itself, with no debt to the sky at all. This is the crucial point, and it changes everything about the fate of the Earth's life. These vent communities are, in a real and complete sense, independent of the sun. They were never lit by it, and never fed by it. And on an ejected Earth, the vents would keep flowing because the heat that drives them comes from the planet's interior, which goes on burning regardless of what happens to the sky. The only question for the vent communities is whether the water around them stays liquid. And beneath a thick, insulating shell of ice, warmed from below by that same inner heat, the water would stay liquid for thousands of years at the least, and near the hottest vents, for very much longer. The vents would go on flowing in the dark, and the life around them would go on living, as though the loss of the sun far above were a rumor from another world. Deeper still, down within the solid rock of the crust itself, there lives a community even more resilient and even less dependent on anything above. It is called the deep biosphere, and it may be one of the largest and least appreciated realms of life on the planet. Kilometers below the surface, in the pores and cracks and thin films of water that thread through the rock, there live immense numbers of microbes, eking out slow and patient lives on the chemical energy of the rock and the water around them, and on the faint but steady energy released by the natural radioactivity of the stone. These organisms already live in total darkness, already cut off entirely from the surface and the sun, already drawing everything they need from the deep warmth of the earth. To them, the freezing of the surface and the loss of the sun would mean almost nothing at all. Their world is the warm rock, and the warm rock would endure. So while the surface of an ejected Earth would die, the Earth as a living world would not. In the buried ocean and in the deep crust, life could continue for as long as the interior stayed warm and the water stayed liquid, which is to say for a very long time indeed. In the sea beneath the ice, that might mean millions of years, until the slow cooling of the planet finally let the ice reach all the way down. In the deep rock, warmed by heat that fades only across billions of years, it might mean something close to as long as the planet itself stayed geologically alive. The sun would be gone, shrunk to a nameless star somewhere in the crowded sky, and life on the Earth would simply go on, quietly, in the dark, in the very places where it may well have begun. It is worth looking a little closer at how the vent microbes make their living, because it is so unlike the way the surface world works. The process is called chemosynthesis, and it is the deep sea's answer to photosynthesis. Where a plant uses the energy of light to build food, these microbes use the energy stored in chemical bonds, drawing on compounds like the hydrogen sulfide that wells up dissolved in the hot vent water, combining them with other substances in the surrounding sea to release the energy they need. From that energy alone, they build living tissue, and that tissue becomes the base of the whole vent food web, the equivalent of the grass and the plankton of the sunlit world. It is a complete and closed economy of life, and its only real requirement is that the planet keep feeding chemistry and warmth up through the sea floor, which the Earth would do for ages yet. The deep biosphere within the rock is stranger still, and its scale is genuinely hard to grasp. When scientists drill down into the crust, into rock that has lain in darkness for hundreds of millions of years, they find it is not dead. It is inhabited, threaded with living cells, sometimes in surprising numbers, all the way down as far as the rock stays cool enough and cracked enough to hold water. By some estimates, the total mass of all this hidden underground life may rival or exceed the mass of all the life on the surface of the planet. It is a shadow biosphere, enormous and slow and invisible, and it has been there all along beneath our feet, keeping its own quiet company with the warm rock. The pace of that underground life is almost beyond imagining. Fed by only the faintest trickle of chemical energy, some of these microbes live so slowly that a single generation, the span from one cell dividing to the next, may stretch across hundreds or even thousands of years. They are barely ticking over, sipping energy so sparingly that they seem almost to stand outside of time. And some of that energy comes from a source that owes nothing whatsoever to the sun or the surface. The natural radioactivity locked in the rock can split apart the molecules of water that seep through it, freeing up chemical fuel that the microbes can use. In this way, deep underground, life is quietly powered by the slow decay of the atoms in the stone itself, a process that would continue undisturbed on a world thrown into the dark. There is a final thought here that gives the whole picture a certain weight. Many scientists believe that life on Earth may have first begun in exactly these kinds of places, in the warm, mineral-rich water around deep-sea vents, or in the sheltered chemistry of the crust, far from the surface and the sun. If that is so, then life on Earth began in precisely the conditions that would let it survive the loss of the sun. The oldest and deepest way of living, the way that came before green leaves and open skies, would also be the way that outlasted them. And as long as the planet's inner heat kept the vents flowing and the deep rock warm, and as long as the slow churning of the crust kept opening new vents where old ones died, that ancient, patient, sunless life would carry on, holding the living thread of the Earth unbroken through the long dark. There is one more reason the deep life is so well suited to endure, and it lies in how little it asks. The creatures of the sunlit surface are built for abundance, for the constant rich flood of energy that green plants pull from the light, and they are helpless when that flood is cut off. The life of the vents and the deep rock has never known such abundance. It has always made do with a trickle, wringing its living from faint chemical gradients and slow reactions, and so it is already fitted, by long habit, to a world of scarcity. When the great energy of the sun vanished from above, this deep life would notice nothing, because it had never drawn on that energy to begin with. It had always lived lean, and living lean is exactly what survival in the dark requires. It is easy, living on the surface beneath a bright sky, to think of the Earth as a world powered by the sun. But a great deal of what makes the Earth a living, active planet comes from within, and none of it would stop when the sun was lost. Deep inside, the Earth is enormously hot. Heat left over from the violence of its formation, when countless smaller bodies crashed together to build the planet, still lingers in its depths. And to that ancient warmth is added a steady new supply, generated all the time by the slow decay of radioactive elements scattered through the rock, elements like uranium and thorium, and a heavy form of potassium, each releasing a little heat as it breaks down. Together these keep the interior of the Earth at temperatures of thousands of degrees, hot enough at the very center to rival the surface of the sun. And this inner fire runs entirely on its own fuel, owing nothing to the sky. That heat is the engine of the solid Earth, and it drives the slow, ceaseless churning of the mantle, the great mass of hot rock that lies between the crust and the core. The rock there is solid, but over long spans of time it flows, rising where it is hottest and sinking where it has cooled, turning over in sprawling, patient currents. Those currents carry the continents on their backs and grind the plates of the crust against one another, and on an ejected Earth they would go on turning exactly as before. The plates would still move. Mountains would still be pushed slowly upward where the plates collided, new seafloor would still be born at the great ocean ridges and swallowed again at the deep trenches, and the ground would still shudder with earthquakes as the stresses built and released. The surface would be frozen and dark, but the crust beneath it would remain restless and alive. Volcanoes, too, would still erupt. The heat that melts rock into magma comes from within, and it would go on doing so, and from time to time that magma would find its way to the surface and break through, even through a mantle of ice. Picture it, a volcano erupting on the frozen earth, lava and ash and steam bursting up through a sheet of ice into a black and airless sky, melting a brief pool of water that would freeze again once the eruption passed. The fire of the Earth's interior would keep reaching the surface now and then, a reminder that the cold and the dark had conquered only the outside of the world, and that its heart still burned. The planet's magnetic field would endure as well, and this is one of the quieter marvels of the story. That field is generated deep in the outer core, where a boundless ocean of molten iron churns and flows, its motion stirred by the planet's inner heat and shaped by the planet's spin. This turning of liquid metal acts as a natural dynamo, generating the magnetic field that wraps the whole planet in an invisible shell. It does not depend on the sun in any way, and so it would continue, the dark and frozen Earth still cloaked in its magnetism, still turning its great dynamo in the deep. What would change is only what the field had to work against. Today it stands guard against the solar wind, the endless stream of particles blowing off the sun, and it is that meeting of field and wind, high in the sky near the poles, that lights the shimmering curtains of the auroras. Cut loose from the sun, the Earth would meet no solar wind, and so the auroras of home would fade and vanish. But the field itself would remain, now sheltering the planet from nothing more than the thin, faint drizzle of cosmic rays that crosses the space between the stars. All of this inner activity matters for one reason above every other, and it ties the whole story together. The same internal heat that raises the mountains and turns the dynamo and feeds the volcanoes is the very heat that keeps the buried ocean from freezing solid and the deep life from dying. It is all one warmth, rising from one source, doing many things at once, holding a layer of the sea liquid beneath the ice, even as it shoves the continents around above. This is why an ejected Earth would not be a dead stone tumbling through the dark. It would be a geologically living world, warm at its core, wearing a frozen shell, its interior going about its ancient business as though nothing at all had changed, and it would stay that way not for years or centuries, but for billions of years, carrying its warmth and its hidden life onward through the night. The sheer amount of heat involved is worth putting into numbers, because it explains why the Earth can stay warm inside for so long. At any moment, the planet is releasing something like 44 to 47 trillion watts of heat from its interior, flowing steadily up through the crust and out into space. In human terms, that is an immense amount of power, many times all the energy that every nation on Earth uses combined. Spread across the whole surface of the planet, though, it becomes that faint whisper we met at the very beginning, less than 1/10 of a watt for each square meter, drowned out completely by the flood of sunlight while the sun was there. The paradox is that this same heat, far too weak to warm the open surface against the cold of space, is more than strong enough to keep a sea from freezing once that sea is wrapped in an insulating blanket of ice. It is not the amount of heat that changes when the sun departs. It is only what that heat has to compete against. The balance of where the inner heat comes from is itself a slow-changing thing. Roughly half of it is primordial, the leftover warmth of the planet's fiery birth, still seeping out after 4.5 billion years. The other half is made fresh, generated continuously by radioactivity in the rock. Because that radioactive fuel is slowly used up as its atoms decay, the Earth's inner heat is very gradually declining over the ages, a little less each 100 million years. But the decline is so slow and the store so great that the planet will stay hot inside for billions of years yet to come. On a world thrown out of the solar system, that inner clock would keep its own time, ticking down over the eons exactly as it would have if the Earth had never left the sun at all. And the great churning would keep recycling the surface of the world. Over spans of hundreds of millions of years, the plates carry the whole crust through its slow cycle. New rock rising at the ridges, old rock sinking back into the depths, the face of the planet made and unmade again and again. On the ejected Earth, hidden beneath its ice, that cycle would continue, and each turn of it would open new vents where old ones had died and expose fresh rock and fresh chemistry to the buried sea. The engine that warmed the deep life would also keep renewing the places it could live. The sun would be gone, but the Earth would go on making and remaking itself in the dark, a planet still building mountains no eye would ever see, still turning a dynamo whose field lit no auroras, still burning, patiently, at its core. Through all of this, the Earth would not travel alone. The Moon has circled the Earth for billions of years, bound to it by gravity, and in most ways an ejection from the solar system would leave that ancient partnership intact. Unless the encounter that flung the Earth outward were extraordinarily close and violent, close enough to tear the two apart, the Moon would remain in its orbit, continuing its slow monthly circuit of the planet exactly as it always had. The two worlds would drift into the dark together, still turning around their shared center, still holding to each other across the same 250,000 miles of space that had always separated them. But the Moon, we know, is a bright thing, and it is bright for one reason only. It makes no light of its own. Every gleam of moonlight that has ever fallen on the Earth is sunlight, caught by the Moon's grey surface and thrown back to us across the dark. Cut off from the sun, the Moon would go dark along with everything else. There would be no more full moon rising golden over the horizon, no more slender crescent in the evening, no more silver light laid across a frozen sea. The Moon would become a black disk hanging in a black sky, betrayed only by the way it blotted out the stars behind it as it passed, and lit, if at all, by nothing more than the faint glow of the stars themselves. The phases would end entirely, for the phases are made of sunlight, the changing view of the Moon's lit and unlit halves, and with no sunlight there would be no lit half to see. The tides, though, would not end, and this is a subtle and lovely point. The tides are not made of light. They are made of gravity, of the way the Moon's pull is a little stronger on the near side of the Earth than on the far side, stretching the planet ever so slightly along the line between them and raising the great, slow bulges in the sea that we know as the tides. That pull would not weaken in the dark. In the early years, before the seas had frozen over, the ocean tides would still rise and fall along the coasts, though they would be simpler than before, for the smaller tide that the sun itself raises would be gone, leaving only the Moon's. And once the surface of the ocean had locked beneath its shell of ice, the tides would not truly stop even then. The Moon's pull would go on flexing the water sealed below and kneading the solid body of the planet itself, a slow gravitational working that would continue for as long as the Moon kept its place in the sky. Over immense spans of time, the long, patient dance between the Earth and the Moon would go on exactly as it does today, needing no sunlight at all. The Moon would keep drifting very slowly outward, a few centimeters further from the Earth each year, as it has been doing for ages, and in answer, the Earth's spin would keep very gradually slowing, the day lengthening by the smallest amount across the eons. These are tidal processes, driven by gravity alone, and the dark would not touch them. The two worlds would keep their timing, the dark planet and its darker companion, falling together through the galaxy, holding to the oldest relationship either of them had ever known, now carried on entirely in the night, unseen and unbroken, long after the sun that once lit them both had faded to a point among the stars. There is a question worth asking about the Moon's pull, because on some other worlds it would matter a great deal. When a moon flexes the body of the planet it circles, that flexing generates heat, friction deep in the rock and the water as the tides rise and fall. On certain moons of the outer solar system, this tidal heating is powerful enough to melt interiors and drive volcanoes and keep whole oceans liquid, doing the work that an internal fire does for the Earth. One might wonder, then, whether the moon's tides could help keep the ejected Earth warm. The honest answer is that they would help only a little. The moon is too far away and its pull too gentle to heat the Earth strongly, and the warmth it added by flexing the planet would be small beside the great inner heat rising from the Earth's own core. The Earth would stay warm inside because of its own fire, not because of the moon. Still, the tides would add their faint share, one more small source of warmth working quietly in the dark. The moon would go on doing one other quiet service as well. Its steady pull helps to hold the tilt of the Earth's axis stable, keeping the planet from wobbling and rolling as it spins. That tilt would no longer bring any seasons, for there would be no sun to lean toward or away from, but the moon would keep steadying it all the same, holding the frozen Earth to a smooth and even spin, rather than letting it tumble. And so the moon, though dark now and silent, would remain a kind of anchor, its presence still shaping the planet in ways too slow and too deep to see. To an eye on the frozen surface, in the years before the air came down, the moon would be the one great thing in the sky besides the stars. It would show no face, no seas or craters, no glow, only a round patch of deeper darkness moving slowly among the constellations, edged perhaps by the faintest starlit rim. Month after month it would make its silent circuit, the single large companion of a world that had lost everything else, keeping the Earth company in the dark, as it had kept it company in the light, faithful and unseen, all the way out into the long night between the stars. It is worth remembering too how the pair came to be, because that history would drift onward with them. The moon was born of the Earth, torn from it long ago in a colossal collision early in the planet's life, and it has been slowly moving away ever since, keeping the Earth company across billions of years. That whole long story would simply continue in the dark, unbroken. The collision that made the moon, the slow retreat, the gradual lengthening of the day, all of it would go on unfolding at its ancient pace, indifferent to the loss of the sun. Two worlds made from a single world, still bound, still parting by inches, still falling together through the galaxy, would carry that shared beginning outward with them into the night. There is a quiet symmetry worth noticing in the pair's shared fate. The moon has always been, in a sense, a world already living the life the Earth would now be forced into, a cold and airless place, with no sea and no sky, lit only by a sun it did not depend on for warmth. It survived that way for billions of years without complaint. Now the Earth would join it in the dark, and the two worlds, so different for so long, would become at last more alike, both frozen, both airless at the surface, both lit only by the distant stars. The bright blue world and its pale grey companion would end their long contrast, matched finally in the cold, keeping each other company as equals in the night. Imagine standing on the frozen surface across the first years of the journey and looking up, watching the sky change. At the beginning, the sun would still rule the heavens, but visibly, steadily diminishing. Month by month it would draw back and shrink, from the wide, warm disk that had lit every sky in the planet's history, to a smaller disk, and then to something too small to show any shape at all, a single point of light, more brilliant than anything else in the heavens but no longer carrying any warmth. It would still be, for a time, unmistakably the sun, the brightest thing in the sky by an enormous margin. But it would be a sun you could look at, a sun that gave nothing back, a cold, bright star where a warm, broad disk had been. And then, Over the years, it would fade further, dimming as the distance opened, sliding slowly down through the ranks of the brightest stars. There would come a time when a person who did not know where to look would no longer be able to pick it out, when the sun had become simply one point of light among the thousands, no brighter than a dozen others, indistinguishable to the eye from any ordinary star. The star that had made the earth, that had warmed every living thing that ever breathed, would take its place quietly in the crowd of the night sky, and the frozen world would go on without it, unable even to tell any longer which of all those distant lights had once been its own. The rest of the sky, strangely, would hardly change at all, at least for a very long while. The stars of the constellations are so tremendously far away, tens and hundreds and thousands of light years distant, that the Earth's slow drift outward would not shift their positions in any way the eye could catch, not for thousands of years. The same patterns that have wheeled over every night of human history, the same shapes that every generation has looked up and named, would keep their familiar forms over the frozen world, unmoved and unchanged. Only very slowly, as the Earth drifted light years from its birthplace across the long ages, would the very nearest stars begin to shift against the more distant ones, and the old constellations begin, gently and imperceptibly, to lose their shapes. The day and night of the planet would continue, in a sense, because the Earth would keep turning on its axis, just as it always had. But they would no longer be day and night in any way that meant anything. The sky would be dark at every hour, at what had once been noon no less than at midnight. The stars would still rise in the east and set in the west, wheeling overhead in the same steady rhythm as the planets spun beneath them, marking out the same span of hours that had always made a day. But no sun would rise among them. There would only be the long night, repeating and repeating, its passage measured out by the turning of the star field overhead, and in the early years by the dark shape of the moon moving slowly through the constellations. In the far future, once the atmosphere itself had frozen and fallen to the ground, the sky would grow sharper and stranger still. With no air to soften it, the darkness between the stars would deepen to a perfect black, and the stars themselves would burn with a hard, unwavering steadiness, never twinkling, never dimming, each one a fixed and brilliant point. The whole light of the galaxy would lie bare overhead, undimmed by any air, a river of distant suns spilled across a black so complete it had no bottom. It would be, in its cold way, one of the clearest and most magnificent views of the universe that any world could ever offer, the frozen planet and the deep sky holding perfectly still together as they fell through the dark between the stars, the one watching the other in a silence that nothing would ever break. The pace of the sun's fading follows the same simple law that governs its warmth. Its brightness, like its heat, falls away with the square of the distance, so that every time the Earth doubled its distance from the sun would grow 4 times fainter in the sky. That fading would be gradual at first, and then, in the way of such things, would seem to gather speed, the sun losing its brilliance faster and faster in appearance as the Earth drew away. Even so, because the sun starts out so overwhelmingly bright, it would remain the brightest object in the Earth's sky for years after the ejection, outshining every star, before at last sinking into their ranks. There would be no single night when it went out. There would only be a long procession of nights across which it mattered less and less, until one could no longer say which night had been the last to hold it as anything special. There is a poignancy in the constellations staying still while the sun alone slips away. Everything else in the sky would remain a faithful map of home, the same familiar figures the Earth had always turned beneath, because those stars are simply too far for the journey to disturb. Only the sun, the nearest star of all, the one the Earth was actually leaving, would move against that fixed backdrop, dwindling and dimming, while all its distant cousins held their places. For a long time then, the frozen Earth would carry an almost unchanged night sky out into the dark, a keepsake of the heavens it had known, with a single light quietly going out at its center. And even in the deepest dark, far from the sun and far from any other star, the sky over the Earth would never be truly empty. The twinkling of the stars would be gone once the air had frozen, for twinkling is only the stir of turbulence in the atmosphere bending their light, and there would be no atmosphere left to stir. But the stars themselves would remain, steady and countless, and behind them the soft combined glow of the whole galaxy's worth of distant suns would lie across the sky like a faint mist of light. The Earth would drift through the spaces between the stars, but it would never drift beyond the reach of their light entirely. Wherever it went in the long night, there would always be that quiet radiance overhead, the gathered shining of 100 billion suns, keeping the frozen world in a dim and gentle light that no distance could quite take away. For those first years, before the cold grew too deep to bear, the fading sun would still mark the great signposts of the outer solar system as the Earth slipped past them. At the distance of Jupiter, it would be a small, fierce point, brighter than any star but showing no disk. By the distance of the far outer world Neptune, it would be fainter still, though even there it would remain far brighter than the full moon had ever appeared, casting a wan, colorless light across the ice. Only well beyond the last planets, out in the great emptiness where the sun's territory gave way to the space between the stars, would that last thin light finally fail to matter, and the Earth pass fully into the keeping of the general night. Once it was fully clear of the solar system, the Earth would settle into the life of a rogue planet, a world that belonged to the galaxy as a whole rather than to any single star. It would coast outward at a steady speed of a few tens of kilometers each second, no longer speeding up, no longer slowing in any way that mattered, simply moving in a nearly straight line through the great emptiness between the stars. Out there, space is very nearly perfect emptiness, and there would be almost nothing at all to slow the planet down. It would carry the motion it had been given at the start onward, patiently, across distances that beggar the imagination, for as long as the galaxy itself endured. At such speeds, the distances are so tremendous that the Earth's progress would seem, by any human measure, almost to stand still. First, it would have to cross the enormous shell of icy bodies that surrounds the solar system far beyond the last planet, a faint cloud of frozen worlds stretching perhaps a light year or more out into the dark. Even moving at tens of kilometers a second, the Earth would take tens of thousands of years merely to pass through that outer shell and leave the sun's country truly behind. And then would begin the far greater emptiness, the true interstellar void, where the distances between one star and the next are so great that the Earth would drift for something like 100,000 years or more before it came anywhere near another sun. And near, out there, is a word that means light years, a gulf so wide that the other star would be nothing but a bright point in the sky, offering no warmth, no anchor, no home. The Earth would drift past it in the dark and simply continue, unclaimed and unslowed, into the space beyond. Yet for all this talk of drifting, the Earth would not truly wander at random through the galaxy. Like the sun before it, like every star and every world in the Milky Way, the Earth would move in a great slow orbit around the center of the galaxy, carried along in the immense rotation of the whole starry wheel. That galactic motion is swift in absolute terms, some 200 kilometers a second and more, but the galaxy is so immense that a single circuit around its center takes something on the order of 200 million years to complete. The Earth's ejection from the solar system would nudge its path only slightly against that grander current. It would remain a citizen of the galaxy, following the same slow rotation as everything around it, one more frozen world riding the enormous, ancient wheel of the Milky Way through the dark. And it would be far from unique in its wandering. The galaxy is thought to hold an enormous hidden population of rogue planets, worlds cast out of the systems that made them, drifting starless and alone through the spaces between the suns. There may be billions of them, perhaps even more planets adrift than there are stars to be seen, an entire dark population moving through the galaxy unseen. Almost all of them are invisible to us, cold and lightless, betraying their presence only on the rarest occasions and by the subtlest of signs. Thrown out of the solar system, the Earth would become one more member of this quiet multitude, one more orphan world crossing the immense distances between the stars, indistinguishable from the outside from any other frozen wanderer, carrying its buried ocean and its patient, hidden life through the long night, unremarkable and unnoticed among the countless others doing the same. It is worth pausing on how hard such worlds are to find, because it tells us something about how alone the Earth would be. A rogue planet gives off almost no light of its own. A young one, still warm from its formation, may glow faintly in heat, but an old and frozen world, like the ejected Earth, would be nearly invisible, a dark speck against a dark sky. The main way astronomers catch sight of these wanderers is by a rare trick of gravity. When a rogue planet happens to drift almost exactly in front of a distant star, its gravity bending and briefly brightening that star's light in a way that betrays the unseen world's passing. Such alignments are fleeting and uncommon, and they reveal each planet only once, for a matter of hours or days, before it vanishes again into the dark. That is how faint and hidden this population is, and it is the company the Earth would keep. The emptiness the Earth would cross is difficult to overstate. If the Sun were shrunk to the size of a grain of sand, the nearest other star would be another grain of sand many miles away, with nothing but void in between. That is the true scale of interstellar space, and it is why the Earth could drift for 100,000 years and still not arrive anywhere. There is a thin haze of gas and dust between the stars, a few atoms scattered through each puff of space, but it is so tenuous that it would do nothing to slow a body as massive as a planet. The Earth would pass through it untouched, sweeping up only the faintest trace of interstellar matter across the ages, coasting on as though through perfect vacuum. There remains one possibility that hovers over the whole long drift, unlikely but not impossible. Across billions of years of wandering, the Earth might, by the rarest chance, pass close enough to another star, and slowly enough to be caught by its gravity and drawn into a new orbit. Were that to happen, the frozen world could find itself once more circling a sun, its ice perhaps beginning, after ages of dark, to warm and thaw. But such a capture requires a meeting so precise and so gentle, out of all the sprawling emptiness and all the great speeds involved, that the odds against it are enormous. Far more likely, by an overwhelming margin, the Earth would simply drift on, uncaptured and unwarmed, keeping its own counsel, carrying its buried sea through the dark for longer than the present age of the universe, one small frozen world among the galaxy's countless quiet wanderers. To set these times against the measures we know is to feel how strange the journey is. The whole of recorded human history, every civilization that ever rose and fell, fits into a few thousand years. The Earth adrift would need tens of times that span merely to clear the outer edge of its old solar system, and a stretch longer still, 100,000 years and more, before it so much as neared another star. Whole species could rise and vanish on the frozen world's hidden shores in the time it took to cross a single gap between suns. The drift is not measured in the lifetimes of creatures or of nations, but in the lifetimes of stars, and against that vastness the Earth would move with a patience it had never needed before, a small dark world in no hurry at all, with all the time in the galaxy ahead of it. And in all that time, the frozen Earth would keep its steady course, asking nothing of the dark, needing nothing from it, simply moving on. The story of an ejected Earth does not end with the freezing of the surface, nor even with the freezing of the air. Those are only its opening chapters. The tale continues across a span of time so long that the freezing seems, in hindsight, almost sudden by comparison. For the deep warmth of the Earth, the inner heat that keeps the buried ocean liquid and the hidden life alive, fades only with the most extraordinary slowness. It is not measured in years, or in thousands of years, or even in millions. It is measured in billions of years, the same immense clock by which the Earth's interior would have cooled had the planet never left the sun at all. For a very long age, then, the frozen Earth would go on holding a sea of liquid water beneath its ice, and life would go on within that sea. How long is impossible to say precisely, but it would likely be many millions of years at the least, and near the hottest sources of heat on the ocean floor, perhaps far longer still. Through all that time, the vents would keep flowing, the deep microbes would keep their slow and patient lives, and the Earth would remain, in the truest sense, a living world, even as it drifted lightless through the dark. The loss of the sun, which had seemed at first like the end of everything, would turn out to be something the planet's deep life simply outlasted, by spans of time that dwarf the whole history of complex life on the surface. But the inner heat does, in the end, decline. Across billions of years, the radioactive elements that make up half of the Earth's warmth would slowly decay away, growing scarcer and yielding less heat with every passing age. The primordial warmth of the planet's birth would keep leaking outward and thinning. And as that deep heat waned, the great engine of the Earth would begin, very gradually, to wind down. The slow churning of the mantle would weaken. The volcanoes would grow quiet and then still. The drifting of the plates would slow, and at last, over unimaginable spans, cease. The dynamo of molten iron in the core would falter and fail, and the magnetic field it had made would fade away and vanish. One by one, across billions of years, the ancient engines of the living planet would fall silent. As the inner heat declined, the buried ocean would freeze deeper and deeper. The shell of ice, which for so long had held its balance against the warmth rising from below, would win a little more with each passing age, thickening downward as the heat that opposed it faded. The layer of liquid water would grow thinner and thinner, retreating toward the last and hottest refuges near the sea floor, until at last, in the far distant future, even those went cold, and the final liquid water of the Earth turned to ice. The deep life, its warmth and its chemistry finally exhausted, would slow and still and end. And the Earth would become, at last, what it had never quite been through all the long ages before, a world frozen through and through, cold to its very heart. This is the true ending of the story, and it is worth seeing clearly what that ending is and is not. The end of the Earth as a living world would not come from the loss of the sun. The planet survives that loss for billions of years, its deep life carrying on in the dark long after the surface has frozen. The end would come instead from the slow cooling of the Earth's own heart, from the gradual exhaustion of the warmth it was born with, over a span of time comparable to the entire present age of the solar system. In a strange way, the ejected Earth would meet almost the same fate it would have met anyway. Even circling the sun, the Earth's interior will one day cool, its dynamo one day die, its inner fire one day fade. The ejected Earth simply reaches that distant end in the cold and the dark instead of in the light, having lost its bright surface first, but kept its living heart for ages longer than anyone would have guessed. There are other paths it might take along the way, most of them unlikely, none of them impossible. It might, across the eons, be captured by a passing star, and warmed anew. It might drift into a dense cloud of gas and dust, or through a crowded quarter of the galaxy, or simply continue undisturbed for longer than the universe has yet existed. But the likeliest future is also the simplest and the quietest. The Earth would coast on through the dark, cooling from the inside out across billions of years, holding its buried sea liquid for as long as it possibly could, and keeping, for a truly remarkable length of time, the fading memory of having once been a warm and living world beneath a bright and steady sun. To feel the length of these times, it helps to remember how old the Earth already is. The planet has existed for some 4.5 billion years, and in all that time its interior has cooled only partway, still hot enough to drive the continents and turn the dynamo today. The cooling that would finally kill the ejected Earth would take a comparable span again, billions of years reaching forward from the moment of its exile. A world thrown into the dark would carry its warmth for so long that whole generations of stars could be born and die in the galaxy around it before its own inner fire went fully cold. The freezing of the surface, which happens in a handful of years, and the death of the interior, which takes billions, stand at opposite ends of an almost incomprehensible gulf of time. The engines of the planet would not fail all at once, but each in its own turn, on its own schedule. The volcanoes and the drifting plates depend on a vigorous churning of the mantle, and they might quiet relatively early as the heat thinned. The dynamo in the core, which needs only enough heat to keep the molten iron stirring, might run on longer, keeping the magnetic field alive for a time after the surface tectonics had stilled. And the deepest microbes, needing only the faintest trickle of chemical energy and warmth, might persist longest of all, holding on in the last warm pockets of rock even after nearly everything else had gone cold. Life would retreat downward and inward as the ages passed, following the warmth toward its final refuges, until there was no warmth left to follow. There is a strange consolation in the shape of this ending. Even circling the sun, the Earth was never going to live forever. Its sun will one day swell and die, its interior will one day cool, its living story will one day close no matter what. The ejected Earth does not escape that fate, but neither does it suffer a worse one. It simply meets its long, slow end in the dark and the cold, out among the stars, rather than in the glare of a dying sun. And it meets that end having proven something quietly remarkable, that a world can lose its star and go on living for ages, that the warmth of a planet's own heart can outlast the light of the sky, and that even cast into the deepest dark, the Earth would remain, for an almost unimaginable span, faithfully and stubbornly warm within. There remains one question that the whole of this journey keeps circling back to, and it is worth ending on, because the answer is more hopeful than one might expect. Could life, real and complex life, even human life, actually survive on a world thrown out of the solar system? The surprising reply that the physics gives is that it is not obviously impossible, and the reason is the same thread that has run through the entire story. The Earth carries its own warmth and its own water out into the dark, and where there is warmth and water, there is at least a chance for life to hold on. The smallest life would very likely endure for ages, as we have seen in the buried ocean and the deep crust, sustained by chemistry and inner heat that never depended on the sun. For larger and more complex life, and for human beings in particular, survival would be far harder, but it would not be forbidden by any law of nature. A people with enough time and enough understanding could, in principle, retreat toward the places where the planet keeps itself warm, down into the deep rock, or beside the hot springs of the ocean floor, or around the heat of volcanic regions where the Earth's fire comes near the surface. From that inner heat, or from the same nuclear energy that powers the deepest reactors, or from the chemistry of the vents themselves, They could draw the warmth and the light and the power that the sun no longer provided. Food could be grown in sealed and heated chambers, lit by lamps that ran on the planet's own energy rather than on sunlight. It would be a narrow and sheltered kind of life, nothing at all like the open abundance of the surface world, but it is a life that the plain rules of physics permit. Scientists have thought seriously about this possibility, not only for the Earth but for rogue planets in general, and they have found that a wandering world need not be a dead one. A planet wrapped in a thick enough blanket, a dense atmosphere, or a deep shell of ice over a warm interior can hold liquid water beneath its surface for billions of years, kept from freezing entirely by its own inner heat, with no star anywhere in its sky. Such a world could carry a hidden, sheltered habitat through the dark for ages. And the Earth, with its enormous oceans and its hot, active interior, is in many ways a natural candidate for exactly this kind of sunless, buried habitability. Life would not flourish on such a world, not in the way it flourishes under a sun. But it could persist, hidden and patient, in the warm dark, for a very long time. And that, in the end, is the quiet and almost comforting lesson of this whole imagined journey. The sun gives the Earth its bright blue skies and its warm seas, its seasons and its sunrises, and its boundless visible crowd of living things, and to lose the sun would be to lose all of that, truly and forever. The surface world, the world we know and love, belongs to the light, and without the light, it ends. But losing the sun would not take away the planet's warmth, or its water, or its deep capacity to shelter life, because those things do not come from the sky. They come from within. Thrown into the dark, the Earth would not become a dead and empty stone. It would become a frozen world with a living heart, carrying its hidden ocean and its patient life through the long night between the stars, warm at its center for billions of years, no matter how far it drifted from the star that made it. So we can let the story rest there, with the Earth adrift and frozen and yet, in the deepest sense, still alive. There is something almost peaceful in it, once the fear is set aside, the image of our world moving quietly through the dark, its surface hushed under ice, its buried sea still liquid and still warm, its oldest and deepest life carrying on exactly as it always had, in the places the sun could never reach anyway. The Earth would not be lost. It would only be changed, wrapped in silence and ice, keeping its warmth folded deep inside, drifting on through the great calm dark with all the patience in the galaxy. It is worth grounding this in what human beings already do today, because the tools are not entirely imaginary. In the volcanic regions of the world, people already draw heat and power straight from the Earth itself, warming their homes and lighting their cities with the planet's inner fire rather than with sunlight. That same geothermal energy, tapped more deeply and more widely, would be one of the very few power sources still available on a sunless Earth, and it would be there in abundance, rising forever from the warm interior. The knowledge of how to use it exists already. What an ejected world would demand is only that it be used everywhere and relied upon completely in place of the sun. The deep sea offers its own proof that such a life can work, in the vent communities we have already met. Around those hot springs on the ocean floor, entire ecosystems of real, complex animals already live and thrive with no sunlight whatsoever, their whole economy built on the chemical energy rising from within the planet. They are a living demonstration that a food web need not begin with light, that warmth and chemistry from the Earth's interior can feed not just microbes but crowds of larger creatures too. On an ejected Earth, those communities would carry on beneath the ice, and they show, in miniature, the shape that any sheltered, sunless living world would have to take. The single thread that makes all of this possible is insulation, the humble power of a blanket. A planet radiates its inner heat away into space, and if nothing holds that heat in, it escapes and the world grows cold. But a thick atmosphere, or a deep shell of ice, traps that warmth and slows its escape, letting the inner heat build a livable pocket beneath. It is the same reason a subsurface ocean can exist at all. The ice that freezes the surface is also the blanket that keeps the depths warm. On a wandering world, the very cold that seals the surface becomes, a little way down, the thing that makes warmth and life possible. There is a strange symmetry in that, the freezing and the sheltering being one and the same act. Perhaps that is the gentlest way to hold the whole idea. A world thrown into the dark does not simply die of the cold. It folds its warmth inward, tucks its life down beneath the ice, and waits, keeping alive within itself the memory and the reality of the warmth it once wore openly. The sun made the surface, but the earth made itself, and the part the earth made would endure. And so we leave the earth where the story leaves it, a frozen world with a warm heart, drifting on through the night, its hidden ocean still liquid far below, still carrying, after everything, a little of the warmth it was born with. There is no need to follow it any further tonight, and no need to carry any of the cold or the distance with you into sleep. Let the frozen world drift on out there among the stars, and let yourself stay here, warm and still and safe. Let your breathing slow. Let your thoughts grow quiet and dim, like a sun softly setting somewhere far away. Sleep well and good night.